Okay, testing, testing. Hello, welcome back to C++. I'm starting on page 237 and particularly section 6.11, function, call stack, and activation records. Now I'll be working through this section, visiting with you, and we'll look at a sample program. But I think this is a very interesting topic to you as new computer science. These topics are introductory, so again, take it slow and feel comfortable. We're just beginning to learn a lot of information. But in this particular section, we're studying introductory topics that are most important mechanisms. Now, I'm sure you have already wondered when a function is called, how does the system remember or know where to return? In some of my diagrams, I've drawn arrows, I've left little dots different times. I say we call the function. When it returns, we return perhaps a value or not to the main calling environment. How do we get that traced back to the code where that function was called and continue with program execution? Well, we're going to learn how that mechanism works. We need to introduce a data structure known as a stack. So some key new vocabulary terms in this section. Introducing a data structure, typically known as a stack. And think about a stack as a pile of dishes. When a dish is placed on the pile, it's normally placed at the top, referred to as pushing the dish onto the stack. Similarly, when a dish is removed from the pile, it's normally removed from the top, referred to as popping the dish off the stack. Stacks are known in computer science as last in, first out, and that's an acronym, LIFO, last in, first out. Some of you who are studying in business may know of LIFO inventory type control measures. Well, in computer science, our stack is known as a last in, first out data structure. So its behavior is that the last item pushed or inserted on the stack is the first item removed or popped from the stack. The function call stack, and sometimes that's referred to as the program execution stack. The function call stack is the data structure working behind the scenes for us, supporting our function calls and the return mechanism. Actually, we don't have to do any programming. It's all behind the scenes, handled for us with our function call mechanism. Last in, first out, that's LIFO, L-I-F-O behavior, is exactly what a function needs in order to return the function that called it. As each function is called, it may in turn call other functions, which may in turn call other functions, all before any of the functions can begin to return their values. Each function must, although, eventually return control to the function that called it. So somehow the system must keep track of the return address that each function needs to return control to the function that called it, or the calling environment. Each time a function calls another function, an entry is pushed onto the stack. This entry, called a stack frame or an activation record, contains the return address that the called function needs in order to return to the calling function. The stack frame. The stack frame or the activation record also maintains the local variables and parameters of that function. So our stack frame or activation record is maintaining the local variables. Remember that any parameters passed to that function are considered local variables, as well as that return address. Non-static local variables exist while the function is executing and are known within that scope or block of code for the function. Local variables must remain active if the function calls another function. But when the called function returns to its caller, the called function's non-static local variables no longer exist. That means that we can no longer make use of that variable. The system has no way of retrieving its value. It's no longer maintained in memory. That's a good thing because, of course, current memory is finite and very costly, so we want to use it wisely. And as long as we no longer need the function variables, they no longer need to be maintained in current memory, which means that that current memory address location can now be reused. The stack frame exists as long as the called function is active. When that function returns and no longer needs its non-static variables, its stack frame or activation record is popped from the stack, and those non-static local variables no longer exist. Since current memory is finite, if more function calls occur than current memory can handle, then a fatal error known as a stack overflow occurs. So let's take a look at our sample program. Figure 612. Now this is a shared data file, so you can create a project and run and execute this program to test it. I'm going to trace the code and try to simulate the stack and activation. Right, glancing at the code, we are beginning with our include file. We're going to use the namespace directive. We have our function prototype so that the compiler knows in advance that the function square requires a passed integer value and it's going to return an integer value. We then come upon main with its begin end block. Main has a local variable a declared to be of type int and initialized with the braces to a value of 10. Main is also going to output a's value, which is 10, some coded material, space squared, colon space, and then it's going to call the function square and pass a's current value. Function square is definition. Function square is expecting an integer to be passed to it. It's going to return a single value of type int, and its processing occurs. Its parameter is considered a local variable. So first, the operating system calls main. Calling main is, this pushes an activation record onto the stack. So we're going to call main. We need a return address. It pushes an activation record onto the stack. So I'm pushing onto the stack. I have these little round figures in the background simulating a dish. So remember, we're thinking of stacking dishes on top of one another. So I'm stacking the activation record for the main function. We know its return address is going to be right here. Main is maintaining a local variable a, and its current value is 10. So on output, A is printed, so we have 10 space squared colon space, and now we're calling square. From function main, before returning to the operating system, it calls function square. This causes a stack frame for square to be pushed to the function stack. This stack will contain the address it needs to return to and will maintain square's local variables. So the return address is going to be our second return address. I'm starting to execute square. We passed an integer value, which is A's value from main. So X is now equal to 10 as a local variable. We process square, and we're supposed to return X times X. Well, X times X would be 100. I'm at the end of the square function. Square needs to know where to return. It's going to return to its calling environment with its value of 100, which will be printed, and we have a new line. Square is done executing, so we no longer need its return address and local variables maintained, so its activation record in the stack frame is popped. And we no longer have access to the variable X's value or the return address or any local variables that might have been established in that function. After square calculates the square of its argument, it needs to return to main and no longer needs the memory for its variable X. So square stack frame is popped from the stack, giving square the return location in main and losing square's local variable value, which is no longer needed to be maintained in current memory. Function main now completes the display of the result by of calling square and prints 100. Prints and displays a new line, and we're at the close brace of main. Reaching the close brace of main causes the stack frame to be popped from the stack, giving main its return address, which allows it to return to the operating system, return its integer value to the operating system, and main's local variables are no longer known or maintained in current memory. I think this is fascinating. This is the challenge for us to understand. It is abstract, I understand that. I hope that my little demonstration of the dishes in the stack frame with the activation records for each of the functions helps make sense for you. As long as you kind of understand that the system is maintaining with some type of a data structure, and that the data structure is a stack where is the light bulb and blasting out behavior, you're doing fine. You will revisit these topics many times and study in more detail and continue with advanced study as you continue your career in computer science. But for now, it's just exciting to know that these things do take place behind the scene for us. And now we're learning a little bit of how behind the scene operates to maintain a secure and logical execution of our program. Our output then, we said that 10 was printed locally in main. We continued with a space squared colon space. Space squared colon space is a string, and then square returned the value of A passed to the square function, and square returned 10 times 10, which is 100. We display that, display a new line, and main returns control to the operating system, and we're ready to press any key to continue. As always, return to D2L Brightspace. We're still working in Unit Chapter 6. Homework, projects, tests, and due dates. All details are listed in your lesson plan. And thank you very much.